Hi, so I'd like to present Dave Watson, who's an infrastructure engineer at Facebook, where he hacks on the Linux kernel. And recently he's done a lot of cool work with malloc, which has caused me pain in my life. Unrelated to the work itself is great. So without further ado, Dave.
Thanks. So the title of the talk is Scaling Server Software at Facebook. My background, my title is engineer. Every single engineer at Facebook's title is actually just engineer. So I'll just give you a little bit of background about what I've been working on. I spent the most amount of time working on Apache Thrift, which is our RPC protocol. That allowed me to dig my fingers into a bunch of different services at Facebook. We have hundreds of major backend services, depending on how you really want to define major. And so I got a broad overview of how all the different ones work and how similar they are, and how we can actually put in some changes that would speed them all up at the same time. So scaling server software, let's take a little bit of a look at what our server software actually looks like. You can compare it to how your software stack actually looks. Surprise, Facebook is a web company. We have lots of HTTP2 servers, mostly running HHVM. Proxygen is our load balancer, also an HTTP server. Apache Thrift, our RPC protocol. We do a lot of memcache. We have McRouter, which is a router for memcache. There's also a lot of databases, things like that. So the thing to notice about every single one of these services is they're all request response services, every single one of them. And that's going to become important later in the talk. We use Linux. Linux is our operating system. We use various versions. We're somewhere between 3.10 and 4.6 right now. By that I mean we have all these different versions rolled out to different services. They just kind of all slowly upgrade over time as they get a chance to do it. So we're relatively modern. All of these services listed here are C++ services. That's not as strongly influencing the topics of the talk, but at the same time it is. They all heavily use the standard template library. And this becomes important because we're going to talk a lot about memory allocation. The standard template library just hammers on the heap. All these things that you're probably used to using if you're using C++, like this std string or the standard shared pointer, vector, these all make tons of tiny little allocations to the heap allocator. And they're just hammering on it all the time, like millions of allocations a second. It's really phenomenal. So we're going to talk about some ways to speed that up. Also, perhaps surprising, our services have a large number of threads. 400 is the average number of threads that each of our services have, which is quite a large number. We could actually go and improve that. A lot of these come from libraries that go and start thread pools. They want to do something, and they want it to happen in the background asynchronously. But whatever library they're using doesn't have an asynchronous interface. So they're like, we'll start a thread pool and then go do some synchronous work in it. That way it's non-blocking. So that happens a lot. There's also just other reasons we have lots of threads. It turns out to not really matter for the most part. Most of these threads are sleeping. They're not doing any work. But it actually does matter in the case of memory allocation, which we'll look at shortly. So the talk is just kind of an amalgamation of a bunch of different things we've tried. Hopefully they're applicable to you. We're going to talk about memory allocation, and then we're going to jump into some scheduling changes we've made, and finally talk about encryption. So I don't know how many people are familiar with how a memory allocator actually works. The allocators I'm talking about are you call malloc, you call free, so something very C-like interface. They're pretty much all implemented the same, at least all the production allocators. There's two parts to them. They're almost invariably split into some main allocator that does the super page allocations. Anything that is larger than one page, you want to ask for 10 pages, you go to one very large central allocator. Sometimes there's more than one split up by NUMA node, but often there's only a single one. And then on the other hand, you have these smaller sub-allocators. Anything that's less than a page in size, it's going to have its own allocation and its own way to do this. And generally that's done with free lists. So a free list allocator, the way it works, is it grabs a single page of memory and it splits it up based on the size of allocation you're requesting. So these class sizes, these would be things like 8 bytes you're requesting, or 16 bytes, or 32. And you could break these up however you actually wanted. This is just like an optimization, a tuning based on whatever your application actually needs. And then the free list allocator is literally just a list of things. These empty boxes here represent things that are free memory that you can go and allocate. So if we say malloc 8 bytes, it's going to say 8 bytes, that's class 0. I'm going to go to that list, pop off a block, and that takes it. That's your allocation. The opposite happens when you call free. Free, it looks up in its metadata, since when you call free, it doesn't actually provide the size of the pointer that it's freeing. So it has to go and look it up in its metadata somehow, figure out that it's class size 0, and then it pushes it onto the free list. And that's the gist of how a free list allocator works. You'll notice this is a O to the 1 operation in both push and pop, malloc free, both very fast, push on and pop off. The thing that we haven't solved at all is fragmentation. You guys have probably heard of fragmentation. Fragmentation is bad. After a while, using a free list allocator, you'll end up with a piece of memory that looks like this. A bunch of holes in it that are used, and a bunch of free blocks that you can go and allocate, but they're all over the place. Fragmentation is bad. It's now your cache locality is very bad. So these things you're grabbing are now sharing a cache line with something else, somewhere else in the system. It's bad because now we can't allocate very large chunks of memory. These could be multiple runs of pages, and maybe we'll want to reuse them for a different size class, and you can't do that unless you compact your heap like this. So of course, the other allocator, the central allocator, it is not a free list allocator. It is a heap, heap allocation or managing heap memory. It has a heap data structure almost invariably, and that's log n. It takes log n time to go and sort your heap, but you end up with a very pretty heap like this. So the fundamental trade-off in memory allocation is how much are we going to send to the central allocator that is going to do the heap defragmenting for log n time, and how much are we going to spend just doing a free list allocation extremely quickly. So the split for every single production allocator that I am aware of, the ones I'm most familiar with would be like the Linux kernel's allocator. It has a binary buddy for the main one, and it has free lists for the sub heaps. Or you have tcmalloc or jemalloc, which both function roughly the same way. They don't use a binary buddy, they use a coalescing central allocator, but it ends up being roughly the same idea. Then each of them has these array lists that are thread local now, that it goes and does array lists when you want to do for small allocations. So how do we make this choice? How much memory do we actually cache versus how much do we send off to the central allocator? It's actually not really a solved question. There's lots of tuning that goes on here. You run your program a bunch of times, try and figure out the best value to do it. It turns out the primary difference between jemalloc and tcmalloc, which Paul had just mentioned in the last talk, is that jemalloc by default caches lots of memory. It will just like cache megabytes in each individual thread without any tuning. It'll say, oh, whatever, 5 megabytes, no problem. We'll just hold on to that till the next time you need it. The flip side, tcmalloc, will do the exact opposite. It has a very small limit per thread. It'll try and flush as much as it can back to the central allocator. So both of these are actually tunable. You could get roughly the same performance from either one. You just have to know that you have to go and turn these knobs. You have to know that they exist to begin with. But perhaps we could do something better with this. These individual thread local free lists are actually not the best because each thread, like we said, we had 400 threads. There's a lot of them. There's not really any limit to the number of threads you can make. In addition, these threads can go to sleep. They could block. They could block on a futex. They could block on some blocking I/O that they're going to do. There's a lot of things they could do. And then this free list that it's holding on to per thread, it can't do anything with it. It's just tied up in that thread and will never be used again until that thread wakes back up and does something. And so that's actually the reason we want to flush very actively back to the central cache. But maybe there's a better way. It turns out the Linux kernel doesn't keep per thread free lists. It keeps per CPU free lists. So this may come with a bunch of benefits for us. Instead of having 400 different free lists, we could only have one per core. So 32, 64, however many cores you actually have, that number of free lists. This is, of course, making the assumption that you have fewer cores than threads, which for us is almost always true. The free lists never become idle now. Presumably you have enough work to go around to all your different cores. You're not keeping your cores idle. So your cores are always using these free lists instead of being tied up in threads that are actually just sleeping and doing nothing. So this could potentially save us lots of memory. So we just went, before we even started doing any work, we're just like, let's go check and see how much memory we could actually save by doing this. It turns out it's a lot of memory. Between 5 and 20% of memory at Facebook is just tied up in free lists, doing nothing. We can't tune these down. Like if we tune them down anymore, we just actually will make our application go slower. We've made the explicit choice that we want to spend memory to make our application go faster and lower our latency. So we can't actually make these go away without somehow sharing the free lists. And that's the idea of restartable sequences. So these have been around for a while. Restartable sequences are a way to make a per CPU data structure. and therefore we can build our per CPU free lists on top of it. There originally the idea was we were going to make something interact with the scheduler in such a way that we are going to make an atomic, even though we didn't have hardware support for an atomic. So these were invented sometime in the late 80s, early 90s. There's several different papers about them that you can go and read. NetBSD actually dropped them into their kernel in 2003, so they actually exist in real code that maybe some people is using. And then Paul Turner from Google was the first person, but now several people have taken a crack at this and realized, hey, we can use these not just for atomic variables on a single uniprocessor machine, but now to make it instead a per CPU data structure across however many cores we actually have. So the proposal was first proposed sometime in 2013 for Linux. There's been a series of RFCs after that of various complexities. And we're going to dive into a few of the specifics and how these actually work. So the main idea is that somehow we're going to interact with the scheduler and say, if I'm in this little atomic section, you need to do something special when you preempt me. In the kernel, it could just turn off preemption, and therefore you have a per CPU data structure. We don't want to do that in user space. We actually like preemption. It's good. Instead, what we're going to say is, if we're in this atomic section, we are just going to restart. Scheduler, when you notice we are here, restart us if you go to preempt us. And that's it. That's the entire idea behind restartable sequences. The trick is, of course, going to implement them. So here's a little pseudocode of what it looks like. This would just be a simple linked list pop. Somehow you tell the scheduler, I'm now in my restartable sequence. We do the pop. At the very last one, we reset the head to the next thing in the linked list, and then we end the section. So the first problem we run into is, how do we tell the scheduler that we're actually in a restartable sequence? There's a bunch of different approaches we could take. You could just record it in a register if we had an extra register lying around, set a flag, or set our restart address more likely, and say, now, scheduler, if you notice that this register has a restart address in it, just jump back to it. We can't do that. We use x86 boxes. There's not very many registers, very few. So instead, we have to take a different approach. We could reuse a register that already exists, for example, the instruction pointer register. That can be used to uniquely identify a section of code, and therefore our little atomic section, and we can use that. That also has a couple of downsides, though. For one, if you're using the instruction pointer, it changes based on as you go through the code, but most importantly, if you want to make a function call, you change the instruction pointer. So you could no longer use function calls in your restartable sequence, which kind of sucks. Also, currently in compilers today, there is no mechanism to say, I want you to compile this little block of code, but I want you to put it between two instruction pointer ranges, like as tightly packed as you can. There's no annotation for that in GCC or Clang or whatever. So you probably have to write it in an inline assembly block, at least for now. The final method that you could do, instead of saying, I want to put this in a register, I want to put this in some sort of thread local variable. I can just use a memory location to put this in. Of course, because we're using lots of threads, we need a thread local to put it in instead. And this will be fine. We'll probably hit L1 cache. It'll be a little bit slower than register, but it'll be fine. This depends on fast thread local variables. I'm not going to dive into the specifics of thread locals and how they actually work, but suffice it to say that if you're statically linking your whole binary together, thread locals are fast. If you don't, and you say, I'm going to dynamically load some shared library, thread locals end up being very slow. And they actually end up also making a function call. On x86, your fast thread locals actually are using a segmentation register, so they go extremely fast because they essentially have hardware support. So let's try and convert our pseudocode from a couple slides ago into something that looks a little bit more real that you might actually write. So we'll start with the last one here. It's probably the most important. So this end section here, this is actually exactly like a compare and swap. Maybe you guys are familiar with lock-free programming. Paul just did a talk on it. It looks very similar. You just say, here's the old value, here's the new value you want it to be. I want you to go and check it. And if so, then set it to the new value. Great. So what are we actually going to write for this end section? This is the part that's actually going to be our assembler. Our inline assembler is going to stick a little code block in there. First thing it's going to do is go in and say, you are now the scheduler. You're not going to, if you preempt us, this is our restart address. So do that. Then we're going to do the compare and swap. And at the end, we're going to say, we're done. Clear out the restartable address. So that allows us to write just one little section of code, a single compare and swap instruction in assembly, and everything else can be in a high-level language. The read here, you could just read the memory and go and use it. This actually has safe memory reclamation issues if you just go and do these reads in a higher level language. It turns out to not be a huge deal in terms of an allocator. I'll talk about it in a little bit. The begin section, though, that actually, sometimes you don't have to do anything, but if you want to make sure your reads are still valid, you actually have to do something there. So what can you do? Well, one approach is we could export from kernel space some sort of preempt count. So, begin section now says how many times, what's the preempt counter for this process? Say it's 100. Now I'll go and do all my reads, and in end section, we'll just verify that that counter was the same. We'll double check, we'll ask the kernel again, what was the preempt count? Is it still 100? Okay, good, I'm good. Everything is still valid. I've still been running on the same CPU the whole time. But if it was different, we'll just automatically restart without actually doing anything in our restartable sequence. So just that is enough to now go and give us a full restartable sequence where all our reads can be in a higher level language. You only get one write anyway, so we only have to write one single end section. Not entirely true. You could actually do multiple writes, but only one of them can actually be the linearization point for the whole algorithm that you're going to go and write. Cool. So these issues, it has safe memory reclamation issues. Turns out to not be a problem if you're just going to write an allocator. The memory you're interacting with was going to be on the free list. It is memory that your allocator allocated for you. The allocator knows if the memory is valid or not, assuming that you're not unmapping memory. So what do I mean by that? All the production allocators don't actually call munmap. It's just too slow. They don't do it. They call mmap to grab memory, and then they call madvise free or madvise don't need to hand the pages back to the operating system while holding on to the virtual memory itself. So for allocator, the memory problem is not an issue at all. Debugging can be a huge issue. So block-free programming in this compare and swap, if we're just like kind of single-stepping through it while a bunch of other threads are trying to access the same data structure, of course, we're going to fail this compare and swap loop, and we're going to go back to the beginning. So we're just going to be single-stepping in a loop forever, which is fine. It's no different than other block-free programming. But now if we jump on to actually doing this in the context of a restartable sequence, the scheduler is going to say, as soon as you set that restart address, now as soon as you're preempted, which is all the time because we're single-stepping through, the ptrace API preempts us, gives control off to the debugger, and now the scheduler is going to restart us. So essentially, you're going to restart on the same address over and over forever. It's not even a loop anymore. It's the same instruction, and you'll have no idea what's going on. So debugging can be an issue. There's a couple ways we could solve this. The way NetBSD solved it in one of the Linux proposals, you could just go and say, this section is now atomic. We're just going to jump over the whole thing, so don't worry about it, which is great. We can no longer debug it, but it was 5 lines of assembly anyway. Maybe it's not that big of a deal. An alternative method, we could actually instrument the debugger ourselves and now say, kernel, don't do any preemption. Let the debugger do it when you've attached with ptrace. And now the debugger will have to push the restarts itself and try and figure things out. This, of course, has the downside of having to interact with the debugger and perhaps more than we would have liked, and changes in the kernel, changes in the debugger, changes in user code, changes in the allocator, changes everywhere to make this work. Finally, the last trick we actually need to make this go is we need a faster get CPU. So if you're making a per CPU data structure, you need some way to index into which CPU you're actually using. For the previous per thread data structures that we might have been using for these 3 free lists, we could just use the segmentation register. That was extremely fast. The kernel sets it for us. Currently, the Linux kernel does not set a segmentation register for a per CPU counter, so we have to go and make a system call ourselves. System call to do that is schedule get CPU. It turns out to not actually be a real system call. It's a VDSO system call, which is just a fast system call. It doesn't make any difference otherwise. Turns out VDSO is still not fast enough. It takes 10 nanoseconds to go and make this call, which is about the same speed as atomic anyway, so we might as well not be talking about restartable sequences and just using atomics unless we can make that faster. Also, right now it is a real function call, so if you're going to use the instruction pointer range, you can't actually make a real function call to get it. So let's say we go and write this whole thing. We're going to write our restartable sequences free list allocators. Now, instead of having thread local free lists, we have per CPU free lists. Like, what have we actually solved by doing this? Fragmentation is now bounded. Presumably, we know the number of CPUs in advance. We know exactly how much memory we're going to hold on to, which is cool. So we can actually predict this in advance. Instead of having to do this filling and flushing and like trying to figure out the perfect size for each thread, if we have homogeneous CPUs, maybe we do, maybe we don't, but you can actually pick the size in advance because your CPU is always going to be doing work. Presumably, one CPU is not going to be doing more work than another, or you know that in advance based on the CPU. The CPUs are never going to go to sleep. I'm also assuming there are more threads than CPUs, so we're not going to lose free lists just to threads like going to sleep and doing nothing. Cache locality actually becomes better. So now your thread, if he is preempted to some other core, he now is grabbing memory that is always on that core. So whoever was last on that core was pulling from the same free list that he now is. So we went and tried this, ran it in production for a while, found a couple of issues that perhaps are a little surprising and you wouldn't have thought of it at first glance. The thread migration issue we've solved it in one way, but now it is actually a problem, but in a different way. So we go and allocate some memory on one core, and now we're preempted and running on a different core. Previously, we weren't sharing the free list. That free list was local to this thread all the time. So if we're grabbing small things that are sharing a cache line, it would always be sharing it with the same thread. So the programmer was in control of if that memory was passed off to a different thread or not. That's not the case anymore. Now we're grabbing from the CPU. So we actually, two threads could be grabbing from the same cache line. And now if one of them migrates, we have this issue of them sharing from a cache line when they weren't before. Also, these things are just slower. They take time. You have to go and tell the scheduler somehow that you're going to be doing something. And you also have to do a check. Was I restarted or not? So you need an extra branch. That just makes them a little bit slower. Here's super rough numbers. Of course, these could change next year. They could change in 6 months. But when you run a micro benchmark, you come up with something like this. A thread local access, extremely fast. A restartable sequence access, a little bit slower. There's a handful of extra instructions, but still extremely fast. An atomic, an uncontended atomic is slower, at least by 2 to 3 times from a restartable sequence. And if you are contended and you haven't sharded your cache lines up in any sort of way, they're extremely slow, very, very slow. Great, so we have something that actually saves us quite a bit of memory. We went and run this in prod for a while on a bunch of different services. Saved us 5 to 20%. Services are using 20 to 40 gigabytes of memory, so saves us a lot of memory that we could be doing something else with. Currently, we've found just a slight latency regression, both because of the new cache line sharing, but also just the extra instructions we're running. So we're working on some ways to try and fix that. This is actually 0.5%. It's not 5%, so half a percent. So we're working on some ways that we could go and fix this. We could say now maybe just have a tiny thread local cache, first of all, or maybe we're only going to do per CPU things that are larger than cache line size. So what are the current status of these things? In Linux, at least, there's been a couple RFCs. You can't actually go and use it yet. You'd have to go and patch the patches in yourself. Patches themselves might have issues too you have to solve. Faster schedule get CPU has been split out as a separate patch set. It looks like it's going to come soon. I'm extremely hopeful because those would be useful even outside of restartable sequences. You could use those just for splitting up atomics themselves to not share cache lines anymore. Cool, so maybe I motivated you guys. You're like, I want to try restartable sequences. I'm going to hack an allocator a little bit. Maybe we don't actually need kernel support to make these go. It turns out you don't. You could just pull some dirty tricks and write these completely in user space and go and use them. Dirty tricks always seem to involve mprotect or for some reason. This one's extremely dirty. You have to go and make a writable code page for every single thread. You then write your commit instruction in the code page itself. And then every time you want to go and use your per CPU data structure, you say, hey, do I own this per CPU data structure? So we're adding an extra branch. If I own this structure, then great, I can go and use it. If I don't, then I have to go and mprotect whoever owned it last. So if he's migrated or he's running somewhere else, he will immediately stop and get a segv. This is, of course, extremely slow. It's going to be much slower than the kernel implementation, but you have to handle an extra segv and you have to handle an extra mprotect. But it's kind of cool because you could go and play with it today without having to wait for anything else. Whew. All right, restartable sequences. We're going to move on and talk a little bit about scheduling. We have a couple major points into our scheduler at Facebook and most of our services. We, of course, have preemption. We've been talking a lot about how we're preempted and going and doing something else. We also have futexes are a major point. We already had a whole talk about that, so that's cool. The last major point that we haven't touched on yet is that epoll is our other major entry point into the scheduler. So we don't do any blocking I/O at Facebook. Everything is epoll. It's non-blocking. We're waiting for events based on whatever epoll tells us is ready. So if you guys are familiar with epoll, like the 20-second overview of how it works is you say to the kernel, here's a list of FDs, probably in our case representing file descriptors from TCP, so TCP connections to someone. Now tell us when any of these are readable or we have writes based on any of them and we've registered for writes. So let us know when someone is trying to talk to us and give us some request, or let us know if we have the buffer is emptied out enough that we're trying to send some data and we want to send it off to someone else. So the way epoll works, depending on your mental model, it's an event loop. So some threads are spinning, actually doing reads and writes on these FDs, and some are actually sleeping in epoll wait, waiting for events. They're not all doing the same thing. So the current way, pretty much every single server is built that I've seen, at least at Facebook and externally using epoll. You grab one connection, you accept some TCP connection, you choose some epoll to put it in. So generally, these are non-blocking things, so you really only need one thread per core. So you have one epoll FD per core, you will have one thread spinning in the epoll loop, epoll waiting. You choose one of them to put the connection and make it go. Why are we choosing a single thread to put this connection into? Well, it turns out what happens when the kernel says, okay, you have bytes to read, it's on this socket on this FD. Okay, who's waiting on it? I'm just going to go and wake them all up. Yeah, it's a thundering herd. So the current implementation of epoll is not great. It would be much better if we could take a single connection, put it in all of our threads, and then whoever is epoll waiting would just, we could wake up only one of them and make it go do some work. That would be a much more efficient use. You could never have unloaded threads that don't have any connections and some that have lots of connections. Also, pipelining is a big reason. Some of the protocols we talked about have pipelining advantages. For example, HTTP2, you can stick multiple requests going down the pipe and get the responses out of order. Our RPC protocol can do that as well. So it would be much better if we could serve these requests on different threads and have them go and process them on different threads. So there's actually a couple different patch sets. Several companies have noticed that this was actually an issue. There's an epoll exclusive flag that has landed recently that we can talk about. And also the kernel connection multiplexer was Facebook's approach to this problem. Epoll exclusive is just a single flag that you're going to hand off to epoll when you say, I want to register for events on this FD. You're just going to say epoll exclusive. Now, whenever you want to notify this FD, only wake up one of them. So you have a bunch of threads sleeping in epoll wait. You're only one of them is going to be woken up to do some work. So completely solves thundering herd issue. We're also only going to try and wake up one that is waiting in epoll wait. So if a bunch of other threads are over here doing stuff, we're going to wake up one that is actually sleeping and waiting. We're not going to try and wait for one of these guys to come around. Since you're putting a single connection in many threads now, you do have to worry about racing issues. So you're just getting a notification here. Now when you're woken up, one of these other threads could come back around that was actually processing some work. And now the one that was just woken up and the one that was already doing work could race and try and read the same FD. So you do have to worry about that a little bit. KCM takes a little bit different approach. I had mentioned back at the very beginning of the talk that all of our services were request response. They're actually we have individual messages that we're requesting and sending responses in. Nothing at Facebook is actually like a streaming service. It turns out we're using TCP for everything, but we only care about reliability and congestion control. We don't actually care about TCP as like a sock stream interface to the kernel. It's actually the wrong interface. We just care about the messages themselves, but don't care about streaming at all. So the main motivator for KCM was let's change the interface a little bit. Let's say we want to keep these things, the benefits that TCP brings us, and instead make a new interface on top of TCP. So KCM is a super simple shim layer on top. It's basically two parts. One part is you teach it about the message boundaries for your message. We do this using BPF. So once the kernel knows about how to break up the messages, it can now give you individual messages using a datagram interface instead of streaming. The second half of the KCM, it's called the kernel connection multiplexer, is the multiplexing part. Instead of having a single connection that we're going to put in a bunch of threads, you make different individual virtual connections for KCM. So that looks something like this. So these yellow boxes at the bottom represent the different virtual connections that now we're going to go put in different threads. So we make one virtual connection per thread, put it in a single thread. Now when we have parsed apart our little messages that are coming from whatever TCP connections we've stuck in the multiplexer on top, we break them into individual messages and choose only a single yellow box to give it to. So now only a single thread is getting the actual message itself. How does this help us? Well, it actually means that now we are only going to wake up someone that's sleeping. So if some people are doing work and some are sleeping, we're going to wake one guy up and make him go and work on that message. So there's no more race anymore. We actually know exactly who's going to receive this message. We're also load balancing pretty perfectly all the different requests that are coming in. Let's take a look at the BPF. I don't know if everyone is familiar with BPF at all. It's the Berkeley packet filter. It's like the latest hotness in the Linux kernel. Everyone's jumping on it for different reasons. It allows you to write some cool user space code and inject it up into the kernel. It's a tiny virtual machine. It actually gets JITted into raw machine instructions and runs extremely fast for most architectures. This is an example of how you break apart a message in HTTP2. It is like one line of code, except it wouldn't fit on the slide in one line. There's not a whole lot to it. You just look up, oh wow, sorry, you can't see it. You just look up how many bytes you actually need to read. You convert from like network to host byte order. And you do some, like you parse apart where it actually is in the HTTP header. So it's actually not very much code. So both of these actually solve our wake up issue. We're waking up pretty perfectly now, load balanced across a bunch of different threads. Messages happening in different threads. Pipelining actually works pretty effectively. Here's some pictures to maybe help explain this a little bit better. So KCM, a lot of different requests are coming in on a single connection in the kernel. KCM breaks them apart into different individual messages using the BPF filter and passes them off as different requests to different threads. So this one, it goes out on, request 1 goes out on the first thread, request 2, second thread, request 3, third thread. The thing to notice here is that both the reading and the actual processing the message is now happening in parallel at the same time across all these different threads. KCM isn't doing anything magical. It's not copying bytes. It's doing nothing. It's just running the filter and saying, like, here's a pointer to the beginning of the message. Here's a pointer to the end. And now we're just going to pass that off to the virtual socket and say, now when you call read, you can read via these pointers. Conversely, this is what epoll exclusive looks like. It's a little bit different. Now this is all user space. Notifications are just coming up to user space, but they can happen in different threads now. So the first thread gets the first part of the first message. Epoll exclusive does nothing about putting messages back together. So thread 2 gets the second half of the message. Then it goes off and processes the first request. Thread 3 reads the full second request and goes off and processes it. So the difference here is that the actual reading from kernel space is not parallelizable. You have to read the bytes in sequential order from the kernel the whole time. You also have to worry about which thread owns that memory. So you have to go and like figure out how you're going to piece back together the first half of the first message and the second half of the first message. The way the kernel does this is using skbuffs. It's like a cool network chained linked data structure that you can have various views into. And essentially you have to go and write something like this in user space. This is actually how we were doing this before, except everything would have happened on a single thread. You would have gotten all these different requests on the same thread, pieced them back together, and then we would have done an additional context switch to pass things off to a different thread. Cool, so they both are different in slightly different ways. I hope we've made it clear now. KCM buffers the full message before it passes it off to you, while epoll exclusive doesn't do that. This actually has upsides and downsides. Of course, adding buffering in places isn't always the greatest thing. If you have large messages, now we're buffering in some place that we didn't actually before, which can be bad. On the other hand, we can parallelize the actual sending up of the data to the user space. The biggest difference I found between these, though, when actually going to implement them in real services was how long it actually took to patch into existing code. So KCM, I said that there was one virtual connection per actual thread, which is the same as we had before. We were tying individual connections to individual threads. So KCM actually fits in that model exactly. Instead of using the real connection and tying it to one thread, we break it up into virtual connections and tie the virtual connection to a thread. So you could drop this in with like 20 lines of code. You go in and say, okay, KCM, like here we go. Here's my BPF program, load it up, make the virtual connections every time you get an accept, and split it up, and you don't have to change the rest of your stack at all. This isn't true of epoll exclusive at all. Epoll exclusive, you have to go and manage the wake-ups now. You have to add a bunch of locking to your code. You have to make everything thread safe, that if you're passing data around on a connection object, you have to make sure every access to it is thread safe. The biggest issue, though, is that if you have other things that are also in the epoll loop that are also tied to that connection, for example, request timeouts, idle connection timeouts for like timer FDs. There's also event FDs if you want notifications for other things. These could now be happening in a different thread from the one that you're getting the notifications in. So now you have to go and deal with trying to lock multiple threads at the same time. And what happens when your connection closes? Now you have to go and close all these different connections in all these different epoll threads. So it's more of a hassle. So my experience, when I went to implement these, KCM took about 2 days, 20 lines of code, was pretty fast. epoll exclusive, I spent about 2 weeks trying to get it to work in our architecture. I was able to make it work. They came out with roughly the same results, but epoll exclusive was much harder to actually use. KCM, this is what our performance results were from going and tossing this in production. It mostly affected tail latency. Of course, these are like scheduling issues where we could have been working on a different thread when we weren't before. So tail latency, the P99, the farthest, the lowest, slowest things, was actually improved by 5 to 10%, which is pretty nice. Almost nothing else changed. Like average latency didn't really change. A load on the system didn't really change. So this is pretty much a free latency win. What about the status of these two guys? These are the farthest along. They've actually both been committed to current kernel trees, so you guys can go and use them today. I think KCM was full kernel 4.6 and epoll exclusive was 4.5. So yeah, please go and try them. Cool, so I'm gonna move on to the last little section of the talk a little about encryption. The one thing I hadn't touched on, but is kind of a little bit of a trick in the last part, KCM, we talked about a BPF program. You had to go and break apart the messages somehow. Of course, if you're sending your data over some sort of TLS or encrypted connection, you have to have access to the unencrypted bytes in kernel space. This becomes an issue for like HTTP2, which of course is always like, is part of the spec that it uses TLS encryption. So if you want to use KCM with HTTP2, you actually have to go and decrypt the bytes in kernel space. So how do we do that? We're just going to go and implement now some sort of kernel module to decrypt TLS, which hasn't existed before. There's a bunch of other reasons you may want to do this. KCM is only one of many. There's a lot of things that are broken right now because you can't actually go and use the decrypted bytes in kernel space. Send, file, and splice are cool system calls that you don't have access to if you're using TLS. You can't just go and send data from the disk off to the network because it's not encrypted. You will have to send it to user space first, encrypt it, and then send it off to the network interface. So that implies 2 copies, one to user space and one back to kernel space. That send file is essentially written to get around this that we don't have access to right now. Splice is similar, except it can send things from generic pipe objects and not just files. So yeah, anything you want to write, like BPF programs, like any sort of random program, there's a bunch of hooks now you could go and use. If you want to do some like encapsulation or something, and you need access to the bytes, like we don't have access to any of this yet. Motivators in terms of performance. Facebook doesn't do a lot of static resources. We're mostly a dynamic company. Like all the things are like interactive on the website, but we do have some static resources like profile pictures or other images. These things take up about 2% of the CPU when they're sent out to the user, doing like copy to user, copy from user. Like literally 2% of our CPU we could save if we had some sort of kernel implementation of a socket. This is not all of our machines. This is just the ones that are serving static resources. So 2% isn't huge. Facebook doesn't do lots of static resources, but it's definitely something that we could go and save. On the other hand, like of the machines that are actually doing TLS, like 20% of the CPU is spent like doing encryption and decryption, which is huge. This is gigantic. We would love to encrypt everything at Facebook. We currently don't because of this number. We only encrypt the things that we can feel like we can't actually encrypt and spend this amount on. So if there was some way to get this number to go down, that would be awesome. The only way we've come up with so far is to somehow offload this stuff from the CPU to some sort of other offload, a NIC offload or FPGA or something else. That's not really the point of this talk, but you would still need some sort of kernel interface to TLS to be able to do that. So we actually went and implemented this. We want to be able to run KCM. That is very tempting, so we're just going to go and implement a TLS socket and see how it goes. This is the least far along of the things I'm talking about. Our current implementation is just to keep the handshake in user space like it's always been. All the things we're talking about only need access to the encrypted bytes or decrypted bytes. They don't actually need access to the handshake at all. We just need the bytes that are coming, that are data messages from the user. So we just go and do the handshake like normal using whatever library you want, GNU TLS, OpenSSL, boring SSL, whatever. And then we hand the FD to the kernel implementation of the socket that looks something like this. Now we make a new socket type, this one called Kernel TLS. We go and tell it that we want what protocols we want to run on it and what FD we want to wrap. So as it turns out, GCM AES is the only one supported in TLS, the new spec that's coming up, TLS 1.3. So that's the only one we went and implemented. That is like 95% of our traffic already, even in the current version of TLS 1.2. So this will probably never support the long tail of old people, but like new specs, it will handle just fine. You bind it all together, and then you have to tell the socket about the things that you actually did the handshake for. So you created a key in the handshake and an initialization vector, and whatever your sequence number is. These usually start as 0, but they can change over time. So you poke those down to the socket. The reason these aren't in the bind structure and instead as like separate sock ops is that they can change. So TLS actually has control messages as well. It could say, I'm going to re-handshake with you, which would change all of these parameters. And the way we handle that is the control messages are just spit straight back up to user space the same way they always were. So that's what the point of the two sockets here. One socket is the same socket we've always had that is handled by our SSL library. And the other socket is the one that's only doing the encrypting and decrypting of user data and sent to the application. This actually makes it somewhat transparent. You could imagine, like, except for these 10 lines of code here, like you could retrofit this into any application pretty easily. You just handed this new socket, and now you can do normal POSIX read, write, send file system calls on it, which is awesome. Previously, you would have to go and do like SSL read, SSL write, and other strange things like that. So this is the least far along. We haven't got this all the way to production yet. We've made it through a bunch of load tests on our services. The load tests show it to be like 5 to 7% faster than what we can do in user space. This, of course, the number will be much smaller, more similar to the 2% number from earlier when we actually go to like throw it into our applications, just because like load tests aren't always representative of what we're actually doing. So how far? We actually have a GitHub kernel module that's up. It's been RFC'd once, so got some good feedback. We're running with that. This is, again, the least far along. This has only had one RFC as opposed to 5 or 10 and some of the other ones have had. The GitHub module currently supports DTLS, which is UDP TLS, regular TLS, which is TCP TLS. And several libraries are supported. We've tested with GNU TLS and OpenSSL. They're both very similar. Also, we got OpenConnect VPN to like roughly run along. So the idea being that you can handle all the control messages in user space still, but hand everything off to your virtual Ethernet interface without having to go through user space at all. Cool, so that's a very quick run through of some of the cool stuff we're trying at Facebook. Restartable sequences for memory allocation, scheduling. We talked about epoll exclusive and KCM, and trying out our kernel encryption module. I think we have lots of time for questions if anyone has any questions. You do a microphone?
Have you measured the difference in energy parameter? In n-dimensional space, you're getting faster, but how's the energy consumption?
I haven't measured energy specifically, but I mean in terms of like CPU cycles should be like a rough proxy for that. So like epoll and KCM are just better scheduling. It should actually go down. Restartable sequences, of course, use more instructions, so I would assume it would go up. And the last one, the kernel socket, assuming you're saving the copies, it should also go down.
You mentioned you're running on the commodity Intel machines, right?
Sorry, I can't hear you.
You mentioned you're running on x86.
Yes, correct.
Have you considered like huge pages for the memory allocation, and if so, does it interact with the NUMA functionality at all?
So I can talk about huge pages of NUMA functionality. I can only speak a little bit too. So current memory allocators, user space ones are not amazing with interacting with huge pages. The reason for this is they call madvise free to give the memory back to the operating system, which essentially creates a hole in your page. So as soon as you do that in the current kernel world, it like says you're no longer a huge page. Like when you free this, you can only free a full page at a time. So pretty much no, we don't use free pages with our allocators at all. I don't know of anyone that does. There's some ideas we've had to try and make the interaction better, but currently it's not amazing. The only NUMA that I'm aware of is your central allocator. Generally, you have one per NUMA node. Otherwise, it does become too much like crosstalk. Cool, thank you.